Hey everyone, Tom here and welcome back to Game Dev EDU. This is part 1 in our Tank Trainer 2D game course. We'll be creating this nifty little top-down shooter. This course is written for complete beginners. However, if you're a little more advanced, you may still find it engaging and helpful. By the end of the course, you'll have a fully functioning prototype that would be a fantastic folio piece, covering things like top-down gameplay, menu options, saving, and so on. I'm super excited to bring this course to you, so let's dive into part 1 where we'll be setting up our project, creating the player and adding movement. We first need to create a new project. Now we've already covered this in detail in our installing Unity video. We'll link that in the description below. So if you're not sure on the process, I suggest going and watching that. Otherwise, just ensure you are using a version of Unity 6 so you can follow along exactly with this course and create a universal 2D core project. Once that new project is loaded, you can start exploring the Unity Editor UI. First, I just want to show you how I like to set up my editor at the moment, and this may change as time goes on. You don't have to follow this, it is very much a personal preference. You can also find presets in the Window Layout tab. I find having my game view and scene view side by side works for me, as I can see changes I make in real time. The hierarchy also doesn't need to take up as much screen space, so we can minimize that a little bit. Other than that, I work with a fairly standard layout, but you find what works for you. I'll also show you how I like to organize my hierarchy. Again, this is personal preference and there isn't really a standard to follow as such. I like to group things into main headings such as player, VFX, cameras, environment, and so on. I find the group of hyphens helps to visually separate the list, allowing me to find things much easier. Something that's important to note for our game objects in the hierarchy is their transform, which includes things like the position, rotation, and scale or size. You'll notice that when I made those new empty parent game objects, the position was set to a random set of coordinates. To avoid confusion and any funny business later on, let's try to get into the habit of ensuring that the position is always set to 0, 0, 0 when an object is created. We can do that by right-clicking the word transform and selecting reset, or you can just also change each number to 0. Along with hierarchy organization, it's also worth mentioning a couple of different ways we could organize the project window, the filing cabinet to hold all of the things in our project. Keeping your project organized is incredibly important. As your game grows, so does the number of files, scripts, prefabs, textures, audio files, etc. Without a clear system in place, finding the right file can quickly become frustrating and time-consuming, slowing down development and causing unnecessary headaches. There are 2 common ways to structure your project, by asset type or by game object or element. Organizing by asset type means creating folders like scripts, prefabs, art, audio, animations, and materials. This approach keeps similar files together, making it easy to find and reuse assets across different parts of your game. For smaller projects, organizing by asset type tends to work best. When you only have a handful of scripts and a few prefabs, keeping everything in separate folders based on the type makes it easy to find what you need. Since there aren't too many dependencies between assets, you don't need to worry about grouping things based on gameplay elements. This approach also keeps things simple, reducing clutter and making it easier for beginners to navigate their project structure. For larger games, a category-based structure, something like player, enemies, UI, weapons, etc., is often more practical. As your project grows, different gameplay elements start having their own set of scripts, prefabs, textures, and animations. Instead of jumping between different asset folders to find everything related to an enemy, for example, you can keep all of its relevant files in one place. This method helps keep things modular, making it easy to work on specific parts of the game without getting lost in a sea of files. It's especially useful for team projects where multiple people are working on different areas simultaneously. For this project, I'll be going with option 1. Once you've decided on how you'll organize your project window, it's time to import the assets that we'll be using. Once you have downloaded and extracted the assets, the link to which are in the description below, all you'll need to do to get them into Unity is drag the extracted folder into the project. To keep things organized, I've gone ahead and created a folder called Asset Packs, and I'll drag the pack directly into it. If we explore that pack now, you can see all of the different options you'll have available to you. So now we're ready to begin building our game. As I showed you in the earlier example, I'll set up my player with an empty parent object with an appropriate name and ensure its transform is set to 0, 0, 0. This parent object won't stay empty for long. We'll be adding components to it such as colliders, scripts, and so on. Following that, we're going to set up a visual as a child of the player parent game object. I like doing it this way as it helps keep things separate and more organized and keeps visuals and logic separate. To create it, right-click on the player parent and select Create Empty and call it something descriptive like Visual. Again, it's important to check that the visual has been created at a position of 0, 0, 0. With the visual selected, click Add Component in the inspector and search for Sprite Renderer. It's exactly as it sounds like, a component that allows us to show a sprite on the screen. You'll notice an empty field that is labelled as Sprite, and this is where we select the visual we want. You can also drag and drop the visual from the project window into this field. Click on the little circle and navigate to the tank image you want. And cool, you should now have a visual element added to your player. If you're super zoomed out like I am here, you can double click on the game object in the hierarchy to zoom into it. That's a handy trick if you ever get lost in the game world in the scene view. In addition to the sprite, we'll also add a collider to the game object. However, let's add this to the parent, not the visual. As I said, I like to keep those things separate. So in the inspector, click Add Component, and in the search bar, search for Box Collider 2D. Make sure you choose the 2D version as we're in a 2D project. By selecting Edit Collider, we can see the collider and then easily edit the properties of it, such as its size. We have a few ways available to us to interact with the inspector with fields like this, such as clicking and dragging left and right on the label. We can also click and drag the collider in the scene, or also just type in the values we want in the number field. I also just realised here that the black tank isn't very visible on the screen, so I'll change it out for the bright orange option. This also shows you how easy it is to change sprites attached to a game object. Our tank also needs a turret, so I'll repeat the process of adding a visual element as a child by right-clicking the parent object and selecting Create Empty. Give it a name to distinguish it from the body visual, and as before, add a sprite renderer component in the inspector. This is a great opportunity now to introduce the handy little toolbar you might have seen floating around in the scene view. The hand is our scene navigation tool, allowing us to move freely around the scene. The arrows are the move or translate tool, allowing us to move objects around the scene. The circle is rotation, which is pretty self-explanatory. This square without an arrow is the rect transform tool, which is the area in which a visual fits. And the square with an arrow allows us to scale the game object. You can also toggle between these tools using the QWERTY keys on your keyboard. So just go ahead and move the turret into an appropriate position and have a play around with those tools. Great, now we have our player set up, it's time to add some code to make it move. Let's begin by creating a folder to house our scripts. So after you've created a folder, inside that new folder, we can right-click and create mono behavior. Give it a name before you click off it, something like Tank Movement Controller. Just creating that script won't do anything for us, even if it was preloaded with code to make our player move. Our mono behavior scripts need to be attached to a game object for them to work. Now we have several ways to do this. You can click and drag the script straight onto the game object in the hierarchy, or with the game object selected, you can click and drag the script into the inspector, Or you can also click the Add Component button in the inspector and search for the script. The way you do that is completely up to you. So now we have our visual and we have our script attached to the player. It's time to actually write some code to get our player moving. Double clicking on the script should open up Visual Studio if you have it installed correctly. Now just briefly, let's go over the anatomy of a C# script. At the top are the using statements, which tells Visual Studio to use different packages built into Unity. We don't really need to worry about this for now. Just ensure that you have using Unity Engine included in your script, which it should by default. Next, we have the words public, meaning our script is accessible to other scripts, class, and the name of the script. You'll see in C# scripts that there are a lot of curly braces. These denote the start and end of a class or a method. The entire class is wrapped in the curly braces, so that means any code for the tank movement controller class you write outside of these curly braces won't run. A mono behavior script is created by default with a start and update method. Methods are just chunks of code that we can write. The start method runs only once, when the script is loaded. And as the comment suggests, the update method runs once every frame. To help you visualize this better, first let's just add some debug.log statements into these methods. These statements allow us to print messages to the console in the editor. So in the start method, let's print script loaded. And in the update method, we can print something like frame running. Back into Unity, and in the game view, make sure it's set to play focused. Then click on the console so you can see any messages and press play. We'd expect to see script loaded printed once, which it does, and frame running continually going up. Perfect! But those messages aren't very useful to us, so let's go back into Visual Studio and delete those log messages. I also like to delete the start and update comments. We don't really need them anymore. For our player movement, let's first set up variables that will control our movement speed and rotation speed. Something to be aware of is that we will need to access these variables from within multiple methods, so they need to be declared outside of any other methods. This ensures they are global and can be accessed anywhere within the class. Now, the keyword private is optional here, as variables are private by default. All this means is that other scripts we create cannot access them to modify the values. Once the variables have been declared, let's have a look in Unity to see if they show up, and you'll notice that they don't. Now, it would be really cumbersome to go back and forth between Visual Studio and Unity every time we want to change the scripts, but fortunately there's a trick we can use. At the beginning of the variable declaration, we can use the attribute serialize field, which allows the variable to be visible and changed in the inspector. So now that our variables are visible in the inspector in Unity, let's also talk about the values here. In the script, in the code, movement speed was initially set to 10 and rotation speed was set to 200. We can now change the values in the inspector, and if you do, you'll notice that they don't change in the code. So it's important to note that the values in the inspector are the ones that are the current value. In other words, they override the values in the script. Alright, so that's enough waffle about variables. Let's just clean this up a bit and get stuck into some more movement code. If you remember from earlier, the update method runs or is called every frame. So this seems like a good place to be checking for player input and applying movement. Now we could write all of the code directly into the update method and it would work just fine. However, it's better practice to break things down into their own methods, which we can then call in the update method. In a method like update that could have lots of things happening, This separation helps to keep the code more readable. So we can create our own method here called something like handle movement, and you'll see an error appear straight away, as handle movement doesn't actually exist anywhere in the script yet, as we've just created it ourselves. The easiest way to create the new method now is to click on the name and press Control or Command on a Mac and the period or dot or full stop button. This brings up a little menu with suggestions of how to fix the error. The one we're interested in is Generate Method. Clicking on that will auto-generate the method for us. If you want to practice creating the method yourself, great. You can see the syntax here and have a go at writing it. Just ensure that when you create the method, it's outside of the start or update method, but still inside the class. In here is where we can now start creating our logic for detecting player input and applying that into the movement. The comments I'm putting in here are a fantastic way to keep our thoughts organized and ensure the code we are writing is achieving the outcome we want. So the first step will be to create local variables that will store the user input values. Next, we check for the actual input, and finally, we'll apply the movement. If you're using the provider's pseudocode, feel free to have a crack at this yourself. Otherwise, just follow along. We'll need 2 float variables to store the result of checking for user input. One will be for the movement direction, either up or down, and we'll initially set that to 0. The second one will be to store the rotation direction, and again set to 0. Remember that this is running every frame, so at the beginning of each frame, the movement and rotation will be 0 unless the player is pressing a given button. So let's get that set up next. For this course, we're using the old input system in Unity. It works just fine for a small game like we are making, and is much more beginner friendly. At the end of this course, we'll create a video outlining some more intermediate techniques, which will include refactoring to use the new input system. The syntax for checking for a specific button in Unity is input.getKey, and then the key code. Wrapping it in an if statement, getKey returns true as long as the key is being held down. Perfect for our case. So if the key pressed is W, or in other words, up, we want the move direction to be positive. So we'll set it to 1. I'll place a comment next to the C# line to explain it in plain English. You don't have to if you're confident with it. Now, if you're astute, you can probably guess our next input check. We want to check if the S key is pressed to move backwards or down on the screen. So we say if input.getKey, keycode.s, which in plain English means if the S key is pressed. Now have a think, what do we want to set move direction to? Well, it's backwards, so we'll set it to -1. Cool, so that's the move direction input done. Let's take a look at the rotation direction. We'll be checking for the A and D keys for the rotation, so if you'd like to have a go at typing those in, feel free to pause the video and give it a crack. We'll use the exact same syntax to check for input. The first one will be checking for the A key, and if that is pressed, we'll set the rotation direction to 1. The final input check will be for the D key, and if that is pressed, we'll set the rotation direction to -1. If you want to make sure this is working, you can add a couple of debug.log statements to print out the values of move direction and rotation direction to ensure the input is being picked up correctly. Remember that because the handle movement method is being called in update, it's running every frame, so we should see either 0, 1 or -1 printing every frame in the console, depending on the keys we press. So going back into Unity and running the game, we can see that when I press any of the WASD buttons, the values change from 0 to 1 or -1. Cool! So now that we're successfully checking for input, the last piece to this puzzle is actually applying that to some sort of movement logic. We've already got our movement speed and rotation speed set up, And now we have either a 0, 1 or -1 value depending on the input pressed. We now just need to perform some sort of mathematical calculation on these values and apply that to the transform of our game object. To do that, we need two more variables to store the result of multiplying the speed and direction together. The first one will be a float, and we'll name it something like movement amount, which will be equal to the move direction that we get from the user input, either 0, 1 or -1, multiplied by the movement speed which we set up earlier. Now this would work just fine, but let's also add another multiplication on here, and that is time.delta time. I'll link the Unity documentation on time.delta time in the description. But for now, just know that any calculation that you want to be accurate no matter the frame rate of your game, you need to include this. For example, if we're moving our player by 15 units every frame, and we don't have the time.delta time multiplication in there, someone who is running the game at 200 frames per second would experience much faster movement than another person who is running the game at 10 frames per second. So time.delta time really ensures that the frame rate doesn't affect the calculation. The second value we need here is also a float, named rotation amount, which will have a similar equation, just replacing the movement values with rotation. Great, so we now have the values that tell our player how much to move and rotate. How do we actually apply this to the player? Well, let's go back into Unity and take a look at the transform component of the player game object. For now, we're going to be directly modifying this component just in code. To demonstrate, by using the move tool and moving the player up and down, you can see the Y value of the position changing. Likewise, using the rotate tool and rotating the player, you can see the Z value of the transform's rotation changing. So these are what we'll be modifying in our code. I'll just reset the transform to 0, 0, 0 and jump back into Visual Studio. Firstly, to modify the position of the transform, there is a built-in method in Unity called translate. To use it, we can say transform, which accesses the transform component of the game object this script is attached to, in this case the player, .translate. You can see the description of this method saying that it moves the transform in the direction and distance of translation. In other words, if we have a movement speed of 15 and press the W key, which would equal 1, then we would move 15 units. You can also see that it requires a vector 3, meaning we have to tell it which way to move on each of the three axes, that being X, Y, and Z. So take a moment to think where we're going to pass in the movement amount variable. If you think back to the example before when I was moving the game object, that was changing the Y-axis. So we say 0 for the X-axis, movement amount for the Y-axis, and 0 for the Z-axis. This ensures that the player will only move up and down when we press the W and S keys. If we'd made a mistake and set the X value to movement amount, the player would move left and right when we press the W and S keys. Not ideal. Let's ensure that this is working correctly. So back in Unity, we can double check you have a movement speed set and hit play. You should find that now when you press and hold the W and S keys, the player moves up and down. If you think the movement is too quick, you can press the pause button and change the value in the inspector to try a different speed out. Find a value that you think works for your project. Something to note is that any changes you make when you're in play mode won't persist into the editor when you press stop, so take note of any changes you make. You can see here my movement speed has changed back to 15. And we're almost there with our playing movement. In addition to modifying the transform position, we also need to modify the transform's rotation. Again, there is a built-in method in Unity, and we can use it by accessing the transform. And the method is called rotate. Again, it takes a vector 3. And if you remember the example from before, we want to modify the Z-axis. So we can say 0 for the X, 0 for the Y, and the rotation amount for the Z-axis. And that should be all we need to do to now have movement working for our player. We'll double check by jumping back over into Unity and running the game. We can still move forward and back, great. Plus we can now rotate left and right by pressing and holding the A and D keys, pretty cool. Testing this out though, it's pretty apparent that our values don't quite work that well together. So I'll hit pause and change those values. I always like to make significant changes first, either double or half, when changing numbers, and continue doing so until I reach a good value. I've found for this project, I like a movement speed of 7.5 and rotation speed of 250. Going back into play mode, we can see that's much better. Of course, since I was in play mode, those values didn't save, so I'll have to make sure I change them again back in the scene view. To clean up the code, I'll just remove those debug statements as we don't need them anymore, but I'll leave all the other internal documentation or comments in there so you can continue to reference it. And there you have it guys, a really simple way to move a player in a top-down 2D game. If you have any questions about this implementation, please do ask in the comments below. Or alternatively, feel free to share your ideas if you're making a different style of game. In part 2 of the course, we'll be adding control to the turret using the arrow keys and implementing a projectile. If this video was helpful, please consider liking it and subscribing to the channel. It would help us out so much. So thanks for watching and we'll see you next time on Game Dev EDU.